This is Dr. Mohamed Refaat, Professor of Physiology. Today, I will gently guide you throughout a very interesting and important course of physiology. It's about the cardiovascular system. As you can see in slide number 2, that the cardiovascular system or the circulatory system is composed of the central pump, the heart, and a number of blood vessels. Through slide number 3, I will take you in a journey throughout this cardiovascular system. You have to take in consideration that my aim has been to tell a story, not to write encyclopedia. Our approach requires the students to think rather than simply to memorize. Moreover, I would like to stress on the point that, as far as I could tell, that I would like to provide a detailed explanation in Arabic to our fellow students to get the full grasping of the meaning. In slide number 4, it's a perfect opportunity to shed more light on the details of the cardiovascular system through this introduction. I could say that the cardiovascular system is composed of a pump, which is the heart, that pumps blood through an extensive closed network of tubes, which are called the blood vessels. The aim of this pumping is to provide adequate pressure as well as adequate blood flow to every organ and to every cell of our body. Moreover, the blood supplies cells with their requirements: nutrition, nutrients, oxygen, minerals, water, and other substances, ions, everything, and carry away the cellular waste products like the carbon dioxide, the urea, the creatinine from the muscles, excess heat, and many others, to eliminate them outside the body through the lungs, the kidneys, as well as the skin. In slide number 5, we will be considering the heart. And the heart is an hollow organ present in the chest. You will need to learn the basic anatomical structures of the heart before we go further. Your heart is a muscular organ about the size of your fist. Your heart is divided into two parts, right and left. The division is preventing mixing between oxygen-rich blood and oxygen-poor blood. In slide number 6, we can see clearly that the oxygen-rich blood is at the left side of the heart and the aorta, and it's red in color, while the oxygen-poor blood is on the right side of the heart and in the veins and the pulmonary artery. In this slide also, we can spot more light upon the blood flow through the heart in steps. So as you can notice, in step number 1, the blood is collected from everywhere in the body into the right atrium by the help of the largest veins, the superior vena cava and the inferior vena cava. So superior vena cava collects blood from the upper part of the body, and the inferior vena cava collects blood from the lower part of the body. After that, the blood must pass through the tricuspid valve, which is the valve separating the right atrium from the right ventricle. When the blood is pumped and pushed by the right ventricle, it will open the pulmonary valve in order to push the blood towards the two lungs for gas exchange. In the lungs, the gas exchange takes place. It gives the blood the oxygen and it takes the carbon dioxide. After that, the blood will return through 4 pulmonary veins to the left atrium. Then it passes through the mitral valve down to the left ventricle, which when it contracts, it pumps the blood through the aorta, opening the aortic valve, and the blood will flow through the aorta and being distributed all over the body. This slide number 7 will give a clear picture about the functional components of the cardiovascular system. Number 1, the heart is composed of 4 chambers, 2 atria and 2 ventricles. Regarding the function of each part of the cardiovascular system, it's very important to remember one function for every single part of this system. I could tell that you have to understand well that the atria, الأذينين, act as blood reservoir. They collect blood and they keep it inside until the ventricle asks for it. So it's a blood reservoir and not a pump. So the atria are reservoir, مخازن للدم. مش مهم قوي البامب فانكشن او المضخه بتاعتهم، لانه they are responsible only for filling the ventricle by 30% of its blood volume. Now, what about the ventricles? They are acting as a pump, strong pump. And you can say that the left ventricle is the body pump. What does it mean? This means that it will pump blood to the whole body. And the right ventricle is called the lung pump because it only pumps blood to the lungs. Then, if we have a rapid, fast look to the arterial system, we can recognize the aorta and the large arteries, and they are very rich in elastic tissue. Therefore, they act as a Windkessel vessels to maintain continuous blood flow to the organs. Then we will go to the muscular arteries. They are distributing vessels. They distribute blood in parallel to every organ. Then, lastly but not the least, we have the narrow arteries and the arterioles. They act as resistance vessels. They provide what we will know later as peripheral resistance. Now, about the capillaries. They act as exchange vessels. As long as they are the only part of the cardiovascular system that contain pores and fenestrations to exchange nutrients, materials, and filter fluids, salts, ions, everything to the tissues and collect back the wastes from the tissues. Therefore, the capillaries are exchange vessels. Then we will end this story by the veins, and we can call them capacitance vessels. This is due to the fact that at any moment 60% of our blood volume is present in the veins. From slide 8, we are going to take a look at the right side of the heart. I could say that it's formed of the right atrium, which receives venous blood from systemic circulation through, as I told you, superior and inferior vena cava. Then delivers it to the right ventricle. The right ventricle pumps blood to the pulmonary circulation through the pulmonary artery. The right ventricle pumps blood at relatively low pressure. It's maximum of about 20 to 30 millimeters of mercury under normal conditions, and is therefore considered as a low pressure pump. On the other hand, in slide 9, we can notice that the left side of the heart is formed of the left atrium and the left ventricle. As regards the left atrium, it receives blood from the pulmonary circulation through 4 pulmonary veins, then delivers it to the left ventricle through the mitral valve, while the left ventricle pumps blood to the systemic circulation through the aorta. The left ventricle pumps blood at a high pressure, maximum of about 100 to 140 millimeters mercury, and is therefore considered as a high pressure pump. Therefore, the muscular wall of the left ventricle is 3 times much thicker than that of the right ventricle, because it acts against high resistance pressure. There is one specific point we like to explore in more depth. Have you ever asked yourself why the flow of blood from atria to ventricles and from ventricles into aorta or pulmonary artery occurs in one-way direction, in one-way forward direction, and is not allowed to flow in the opposite direction? In this slide number 10, we can easily answer this question by telling the fact that this story is achieved by the presence of cardiac valves. So the blood flow through the heart is regulated by 4 cardiac valves. First of them, the atrioventricular valves, the AV valves, صمامات القلب, which prevent backflow of blood from ventricle to atria. The mitral valve in particular, which is bicuspid valve, it has two cusps only, two leaflets only. This mitral bicuspid valve is present between the left atrium and the left ventricle, while the tricuspid valve is present between the right atrium and the right ventricle. The leaflets or cusps of these valves are attached to papillary muscle, which is rooted in the wall of the ventricles, and they are, by the help of chorda tendini, this prevents the prolapse of the leaflets in atria when the ventricles contract. If this happens, this means failure of the valve. As far as I could tell, the semilunar valves, on the other hand, which prevent the backflow of blood from the aorta to the left ventricle, aortic valve, and the pulmonary artery to the right ventricle, pulmonary valve, they are semilunar valve because the name comes from the fact that they are their leaflets looks like half moon. This graph on slide 11 gives you a top look at the heart valves. As you can notice that on the right side we have the tricuspid valve, صمام ثلاثي الشرفات له ثلاثة ضرف, and on the left side we have the bicuspid valve or the mitral valve, ثنائي الشرفات وهو الصمام الميترالي. Then if you look carefully, you can notice two other thin smaller valves called the semilunar valves, as I told you. One of them is the aortic valve, but keep in mind it's tricuspid, ثلاثي الشرفات, and the pulmonary valve also it is ثلاثي الشرفات. And this will show you a top view for the four valves together. As you can notice, on the right side we have the tricuspid valve with three cusps, ثلاثي الشرفات. On the other side, the bicuspid valve, it is the mitral valve, it's a bicuspid valve, شرفتين فقط. Then we have the semilunar valves, the aortic and the pulmonary valves. They are smaller and thinner valves, but they are also tricuspid valves. Slide 12 leads me to the next point, in which I would like to tell that the heart is viewed functionally as two pumps, with the pulmonary and systemic circulation situated between the two pumps. The pulmonary circulation is the blood flow within the lungs that is involved in the exchange of gases between the blood and the alveoli. Take in consideration a very important remark here, that the pulmonary artery in blue color is the only artery in the body that carries deoxygenated blood, لأنه لسه لم يمر على الرئتين لكي يتشبع بالأكسجين، فهو الشريان الوحيد اللي يحتوي على دم أزرق لأنه لم يتشبع بالأكسجين. The pulmonary artery is the only artery that carries deoxygenated blood. The systemic circulation is composed of all the blood vessels supplying the organs, excluding the lungs. The blood flows through arteries, arterioles to reach the capillaries, where it exchanges materials with the interstitial fluid bathing the cells. Blood then flow back to the heart through the veins. If you look at the slide 13, you can notice that there are actually two circuits, both originating and terminating in the heart. We have the pulmonary circuit, which is called lesser circulation, and the systemic circuit, which is called the major circulation. Slide 14, it shows you that actually we have two hearts. عندنا قلبين مش قلب واحد. Right heart and left heart. القلب الأيمن والقلب الأيسر. This also will shed more light upon the fact that we have two circuits. The pulmonary, الدورة الدموية الصغرى, and the systemic, الدورة الدموية الكبرى. At this moment, in slide 15, I would like to give a clear picture about the arrangement of the cardiovascular system. I could say that the pulmonary and systemic circulation from the above graphs are arranged in series with each other. يعني على التوالي. يعني تخلص البلمونري سيركوليشن تصب في السيستميك سيركوليشن. السيستميك سيركوليشن يخلص يرجع تاني للبلمونري سيركوليشن. يبقى على التوالي. This in series arrangement requires that the blood pumps per unit time by the right ventricle into the pulmonary circulation should be equal to the blood pumped per unit time by the left ventricle into the systemic circulation. بمعنى ان عشان هذا يتحقق اللي على التوالي لابد ان كمية الدم التي تخرج من البطين الايمن الى الرئتين تساوي كمية الدم التي تخرج من البطين الايسر الى الجسم كله. فهذا يجب أن يؤخذ في الحسبان. Let me just say that in another way. The cardiac output from the right ventricle equals the cardiac output from the left ventricle. يعني كمية الدم اللي بتخرج من البطين الأيمن مع إنها تذهب إلى اللنج فقط فهي تساوي كمية الدم التي تخرج من البطين الأيسر مع إنها رايحة للجسم كله. It will supply the whole body. Keep that in mind. Slide 16 will tell us that the most organs of the body receive their blood supply from the aorta, and the blood leaving these organs enters the venous system to return to the heart through the superior and inferior vena cava. Therefore, the circulation of most organs of the body are in parallel, على التوازي, to each other as shown in the figure. This figure in slide 17 shows us the in parallel arrangement of arteries supplying each organ of the body. At this moment, I would like to give a clear picture of how the in parallel arrangement will make it possible to, number one, increase or decrease the blood supply to a particular organ without affecting blood supply to other organs. I give you one example. Like when we are making muscular exercise, we increase the blood flow to the skeletal muscles during this exercise, playing football match for example, while the blood flow to other organ like the brain is not affected. This is one point. بمعنى انه لما بعمل على التوازي فكل اورجان جايله الارتري بتاعه جايله every organ receives its own artery. So I can constrict or dilate, اقدر اوسع او اضيق الاوعية الدموية بتاعت هذا العضو او الاورجان على حسب احتياجاته. واعطيت مثل واضح وضوح الشمس في ضحاها انه لما نكون بنلعب ماتش كورة او ما نكون بنعمل ماسكولار اكسرسايز فنحن في اشد الحاجة لتزويد العضلات بكميات كبيرة من الدم، ومش ضروري ان انا ابعت دم للمعدة او للمخ. يبقى اذا كل اورجان عنده الشريان بتاعه والشرايين الصغيرة والشريانيات اللي نستطيع ان احنا نتحكم فيها اتساعا او ضيقا على حسب حاجة هذا العضو. Another important point which at my mind is very 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 important, which is that we can guarantee, نضمن, that every organ can get its own fresh oxygenated blood. This blood doesn't pass by other organs before, by any other tissue before. So the blood will come to every organ in its own specific artery fresh. What do you mean by fresh? Means it is oxygenated. What do you mean also? I mean that this blood does not pass by other organs before. وبالتالي هناك مثل من أمثلتي إنه إن كان هناك عمارة وهذه العمارة فيها 10 أدوار، كل شقة ليها ماسورة المياه النقية اللي هي تمر ليها مخصوص من الماسورة الأم. مش معقول سكان الدور الرابع ياخدوا مية مرت على سكان الدور الأول وغسلوا فيها واستحموا فيها وتوضوا كل الكلام ده. يبقى لازم كل عضو ياخد الوعاء الدموي بتاعه. وبضمن الكلام ده ازاي؟ ان يكون الترتيب على التوازي، كل واحد موازي للتاني. So I can say it in other words that the second scientific importance of the arrangement in parallel is that every organ can guarantee a fresh blood supply. This blood does not pass by any organ before. But bearing that in mind, you have to know one important fact, that the liver is exception. How? The liver receives a double blood supply. This is very important anatomically, surgically, physiologically, by all means. It receives part of its blood supply from the aorta in parallel to other organs. Okay, that's right. While it receives a part of its blood supply from the venous blood of the gastrointestinal tract in series. This means that the blood coming from your intestine will pass through the liver first. Why is that? Because the liver is the site for metabolism. In slide 18, after our scientific understanding of the heart, have you ever asked yourself why our heart contains 4 chambers? The heart structure is easy to understand if you remember four basic facts: that the heart must pump blood to the body, and also it must pump blood to the lungs. In the meantime, the heart must receive blood from the body and must receive blood from the lungs. That's why the heart has four chambers. This is the answer. One of each of these function. Slide 20. At this moment, I would like to cover the electric activity of the heart. It's a very important subject and it needs high degree of concentration. In order to understand this electric activity of the heart, you need to be focused, you need to be determined, you need to be hopeful. It's good to remember that the cardiac myocytes, the cardiac muscle cell, have a resting membrane potential of about minus 90 millivolt. The resting membrane potential is determined by, number one, as you know from your previous studies in the nerve and the muscle, the concentration gradient of positively and negatively charged ions across the cell membrane. Sodium is always out and potassium is in. Number two, the relative conductance or permeability of the cell membrane to these ions. As you may remember, maybe forever, that the permeability during rest to potassium is much higher than the permeability for sodium. Number three, the ionic pump that transport ions across the cell membrane. As you might remember that we have the sodium-potassium pump, and I would like to add the calcium ATPase pump. But before we go in depth, if you look carefully to slide number 21, you can see a summary, and it's, by the way, it's very important to know these facts. About this is about the types of ion channels in the cardiac muscle. You have to remember that we have voltage-gated sodium channels, voltage-gated potassium channels, voltage-gated calcium channels, which are of two types: transient T channels and long-lasting L channels. Transient means that it will open and close very rapidly in a very fast way, while the long-lasting will remain opened for longer time. But you have to keep in mind that also we have sodium leak and potassium leak channels, means that they have no gates. The ions can move freely through these channels. This portray or graph in slide number 22 shows you the different types of the ion channels inserted into the bilipid membrane, and some of these channels are open and some of them are closed, as you can easily notice. In slide number 23, there is something new we need to notice about the resting membrane potential in the cardiac myocyte or the myocardial cell. Number one fact, that the efflux of potassium along a concentration gradient during rest. This occurs through inwardly rectifying potassium channels. ومعنى rectifying means correcting. rectifying means correcting يعني بتصلح حاجة. which are open at negative membrane potential. The equilibrium potential for potassium is, as you may remember, minus 94 millivolt. And the membrane is 20 to 100 times more permeable to potassium than sodium. So you have to realize that the resting membrane potential, which is minus 90, is very near to minus 94. On the other hand, we can see that there is influx of sodium along concentration gradient from outside to inside through the leak channels. However, the conductance under resting condition of sodium is low, and therefore it contributes a little to the resting membrane potential. And you may remember that the equilibrium potential for sodium is plus 61 millivolt. During rest, the sodium-potassium electrogenic pump is active day and night, 24/7. This pump mechanism pumps 3 sodium out and in exchange for 2 potassium pumped into the myocyte. On slide 24, this graph clearly shows you the different types of channels for each type of ion, and you can notice that there is an exchange pump between the sodium and calcium. These channels are very specific, متخصصة. يعني هناك قنوات ليست كالقنوات، قنوات للصوديوم تتعامل مع الصوديوم، قنوات للبوتاسيوم، قنوات للكالسيوم فقط، لا يدخلها أيونات أخرى. Slide 25 shows that the channel, sometimes it is open, sometimes it is closed. Slide 26 reminds you by the most famous pump in our body. In every cell, they are acting 24 hours, and it is the sodium-potassium pump acting as a ratio 3:2. It transports sodium, it pumps 3 sodium ions out in exchange for 2 potassium. At my mind, the figures and the illustrations are very important to help you understanding the matters deeply. Slide 27 shows that the resting membrane potential of minus 90 millivolt is very near to the potassium equilibrium potential. Slide 28 shows clearly the leak channels for sodium and potassium, as well as the sodium-potassium exchange pump. Slide 29 shows that how the sodium-potassium pump corrects the effect of leakage of ions across the myocyte cell membrane. If you take a look to slide number 30, it's very easy to remember that during rest, the potassium permeability is much higher than the sodium and the calcium. On the other hand, when we start stimulation of the heart, a state of depolarization will develop when the potassium channels will close and the sodium as well as calcium channels will widely open. In fact, in slide 31, we want to tell 3 important facts about the pumps and the exchangers on the myocyte membrane, which can keep the electric activity and maintain it without any disturbance. Number one, as all of you know, that we have the sodium-potassium ATPase pump, this electrogenic pump acting at a ratio of 3 sodium to 2 potassium. Number two, we have the calcium ATPase pump that pumps calcium out of the myocytes to prevent the accumulation of large amounts of calcium in the cell. In the meantime, we have a sodium-calcium exchanger that exchanges 3 sodium for 1 calcium. It should be noted that this exchanger can operate in both directions, depending on the membrane potential and the concentration gradient for the ions. For example, if excess calcium ions are present inside the myocyte, then the sodium-calcium exchange can move calcium out of the myocyte and bring sodium inside. However, if the intracellular sodium concentration is increased by inhibition of the activity of sodium-potassium ATPase by a famous drug called digitalis, used in treatment of heart failure, the sodium-calcium exchanger will move sodium out and brings calcium inside the myocytes. Once the myocyte got its enough calcium, it will beat strongly. This is a fact. It's obvious from slide 32 that the ion channels and the transporters, as well as the pumps and the exchangers, are working all over the time. Slide 33 shows indeed the presence of these exchangers and pumps on the cell membrane of the cardiac myocyte. SCA node is the natural, normal pacemaker of the heart. Slide 35. It's well apparent from this diagram and curve that the SCA node, which is the normal pacemaker of the heart, starts slow, spontaneous, diastolic depolarization until it reaches certain threshold. Then an action potential develops, showing an upstroke. On reaching its peak, it will go down to show repolarization and return back to the beginning point. In fact, this curve is very important, and I would like every student to know by heart how to draw it by himself. To start with, we must say that the SCA node has unstable resting membrane potential. It never stops at a resting level, waiting for any other cells to stimulate it. Why is that? Because the SCA node is a pacemaker. And you have to understand that the unstable resting membrane potential starts from minus 60 or minus 55 millivolt. Spontaneously, without any stimulation, without any external stimulation, the SA node starts slow process of depolarization. Therefore, the SA node is called slow response muscle fiber. Of course, SA node is a muscle, not a nerve. It is a muscle fiber. This slow depolarization will take place until we reach threshold, عتبة. لابد ان احنا نوصل لهذه الثريشولد او العتبة ثم نتجاوزها ونتخطاها بعملية rapid depolarization اللي هي بنسميها الابستروك اللي هو الاسcending limb بتاع الكيرف. Then after reaching the peak, بعد ما نوصل للقمة لابد ان يحدث repolarization. طبعا هنا المسؤول عن الديبولاريزيشن هو الكالسيوم انفلكس، حاجة تميز الاس نود، والمسؤول عن الريبولاريزيشن هو البوتاسيوم ايفلكس. عندما ينتهي الريبولاريزيشن لا تجلس الاس نود هادئة في حالة ريستنج ميمبرين بوتنشال، ولكنها تبدأ بيت جديدة، ضربة جديدة، اكتيفيتي جديدة، ولذا ليس لها ريستنج ميمبرين بوتنشال ثابت ولكنه متغير، وعشان كده بنسميه unstable resting membrane potential. In slide 36, it's very important to know a very comprehensive idea about the cardiac conduction system. As I told you before, that the pacemaker is the SA node. It is a specialized muscle tissue which is located at the top of the right atrium on the posterior surface, exactly near the opening of the superior vena cava. And as you may remember, I told you that the SA node is the pacemaker of the heart. It initiates, it is self-excitatory, means it excites itself. It is the first part of the heart to be awakened. It is the first part of the heart to be depolarized. It is the first part of the heart to start action. So it will activate other places in the heart by spreading its cardiac impulses through the right and the left atria until it will reach the atrioventricular node, as you can see, the AV node at the bottom of the right atrium. From this AV node, the impulses will spread into bundle of His, or the atrioventricular bundle, which is present in the interventricular septum, as you will know. Then, as we know that we have two ventricles, so this bundle of His should give two branches, right and left bundle branches, which will end by very small fibers called Purkinje fibers that will supply every individual ventricular muscle fiber. إذن الكاردياك كوندكشن سيستم ده جهاز التوصيل الكهربي في القلب. وقلنا أن القلب يعتمد على نفسه في بدء الإشارة الكهربية. The heart depends on itself in initiation of the cardiac impulse. And to prove that, if you cut the heart of the animal and put it on a table, it will continue beating for some time. This means that it doesn't depend upon the nerve supply. Its activity is myogenic, as I told you, and not neurogenic. Only the nerve supply is the regulate the rate of the heart. You want to accelerate the heart, you want to slow the heart. So the sympathetic and parasympathetic nerves, as you know, can control the speed of the heart. But the pacemaker صانع الحركة وصانع الألعاب مثل لاعب كرة القدم, the playmaker and the pacemaker is the SA node. And like the train which can run on a railway, the cardiac impulse must have a conducting system. يبقى زي القطار اللي هو لابد أن يجري على القضبان، وإذا ما خرج عن القضبان لا يستطيع أن يسير. فهنا تسير الكاردياك إمبلس، ولكنها لها مسار محدد ولا بد أن تعرفه معرفة جيدة ولا تخطئ فيه أبدا. والمسار هو من الاس نود إلى الاي نود، وفي أثناء هذا يتم تنشيط الأتريا رايت اند ليفت أتريا، الأذين الأيمن والأيسر. Then you can go from AV node to the AV bundle. His bundle has two branches, right and left bundle branches. And we end وننتهي بالبركنجي فايبرز اللي هي هتغذي بقى كل عضلة من عضلات البطين أو الفنتركل. In slide 37, I am repeating what I have already said in the previous slide, that the cardiac conduction system is formed of, number one, the sinoatrial node or SA node. It is located in the wall of the right atrium at the junction of the superior vena cava. It is connected to the AV node by 3 internodal tracts. This is new fact. Before they thought that there is no bundles or tracts between SA node and the AV node, and the impulse will spread through the atrial muscle itself. But now it is sure that there is 3 internodal tracts connecting SA node and the AV node. Number 2, the atrioventricular node, the AV node, it is located at the posterior lower part of the interatrial septum, and it is continuous with the bundle of His. The AV node can act as secondary pacemaker if the SA node is damaged, but it works at a slower rate. So if we take in consideration that the sinoatrial node or the SA node starts by sending signals or impulses around 70 to 80 beats per minute, the AV node can act as at a lower level, can act as a pacemaker at a lower level. Its rate is only 60 beats per minute. Slide 39. When it comes to the pacemaker potential, we can say that this type of action potential is present only at the SA node and the AV node. And it's very important to stress upon the fact that it is called slow response action potential, because the pacemaker cells can spontaneously and slowly start depolarization and regularly initiate action potentials, and are therefore responsible for 2 cardiac muscle properties: automaticity and the rhythmicity of the heart. In slide 40, I repeat again that you have to remember, maybe forever, that the SA node is the normal pacemaker of the heart. and it has unstable resting membrane potential. The number is important at minus 50 to minus 60 millivolt. It is self-excitatory and is the first part of the heart to start slow depolarization till reaching the firing threshold. إذا ما نريد معرفته عن الاس اي نود أنها صانع الحركة، إنها التي تبدأ من نفسها النشاط الكهربي في القلب، غير منتظرة تنبيه من أي عصب، لأنها قادرة أنها تبدأ slow depolarization ولكنه يوصلها إلى العتبة الفارقة اللي هي الفايرنج ثريشولد. فايرنج بقى هتنطلق بقى شرارة الإمبلس وتعمل أكشن بوتنشال. إذن هي أول جزء يستيقظ في عضلة القلب، ومن يستيقظ أولا يتحكم في كل القلب. هذه هي شريعة ما يحدث في عضلة القلب. SA node is the natural normal. Slide 41. As a matter of fact, if you look carefully to this curve, it will show you the phases of the pacemaker potential, and you can notice that it's composed of 3 phases only, starting by the phase 4, which represent the diastolic depolarization. Then phase 0, it's the ascending upstroke limb. Then phase 3, and at the end of phase 3, phase 4 immediately starts. Phase 0 represents depolarization, and phase 3 represents repolarization. Through slide 42, I want you to have a look to the curve, because it will explain to you the ionic basis of the pacemaker potential and the action potential in the SA node. Let's start by a funny fact that in case of hyperpolarization, there are some newly known channels called funny channels are discovered. They are present in the SA node, and why we call them funny channels? Because they are not supposed to be opened at this voltage of minus 60, but it happened that it is opened and it allows slow sodium entry, starting the initial part of the slow diastolic depolarization. Then, to complete this pre-potential, the calcium channels, the transient calcium channels are open, and the calcium influx will complete this slow depolarization. When we reach the threshold, another type of calcium channels, which are called long-lasting calcium channels, will open and will continue the upstroke limb of this action potential. After reaching the peak of this curve, the calcium permeability is gradually decreased, while the potassium permeability increases markedly, causing the repolarization part of this curve. It's now the time to talk about the different phases of the pacemaker potential and the action potential of the SA node through slide 43. To start with phase 4, And we said before that it's a spontaneous slow depolarization, which is called the prepotential. This phase occurs as follows. At the beginning of this phase, the membrane potential is about minus 60 millivolt. At this potential, gradual depolarization starts due to influx of sodium. Two mechanisms contribute to this inward calcium current. Number one, activation of a special type of sodium channels known as sodium funny channels. I told you before. And the inward sodium current they conduct is known as funny current. الحقيقة أننا لم نكن نتوقع أن تكون هناك قنوات للصوديوم مفتوحة عند الممبرين بوتنشال ماينس 60 ملي فولت، ولكن عندما اكتشفنا هذا صار شيء غريب funny، ولذا سميت funny sodium channels. As long as these funny channels are regulated by intracellular cyclic nucleotide cyclic AMP, that's why these channels are also known as HCN channels. HCN channels meaning hyperpolarization activated cyclic nucleotide regulated channels. Slide 44 is a very nice simple slide showing you the funny channels on the cell membrane of the SA node, and beside it the T-type calcium channels, the transient type, the fast type of calcium channels. And as you can notice that the funny channels are regulated by the cyclic AMP. Slide 45. As far as you could remember, that we have said that as the membrane potential reaches about minus 50 millivolt, another type of channels called the transient or T-type calcium channels open. We have said that they are called transient because they become rapidly inactivated after they open. Calcium enters the cell through these channels down its electrochemical gradient. This inwardly directed calcium current further depolarizes the cell to minus 40 millivolt, which is the threshold. Slide 46. It's good to remember what I have said about phase 0, the ascending upstroke of the action potential. As the membrane is depolarized to the firing level about the threshold of minus 40 millivolt, another type of calcium channels opens. These are known as long-lasting or L-type calcium channels. They are called long-lasting. Why? Because they become inactivated slowly after their opening. Opening of these channels causes more calcium to enter the cell, and it's responsible for phase 0 of depolarization. And due to the fact that the movement of sodium through these channels into the cells is not so rapid, the rate of depolarization or the slope of the phase درجة الميل بتاع الكيرف of phase 0 is much slower than found in other types of cardiac cells, as we will see later. Therefore, the pacemaker action potential is referred to as slow response action potential. يبقى هنا عرفنا لماذا السبب في أن الاكشن بوتنشال بتاع الاس اي نود بيسمى سلو ريسبونس او الاستجابه البطيئه او النسيج ذو الاستجابه البطيئه، لانه يعتمد على نوع من قنوات الكالسيوم التي تعمل ببطء وليس بسرعه، وتسمى ال تايب كالسيوم تشانلز. وهنا أؤكد على حقيقة أننا عرفنا بالفعل ولا ننسى أبدا أن في الاس نود هناك نوعان من الكالسيوم تشانلز. We have T type calcium channel and L type calcium channel. Remember that. 47. Taking in as much knowledge as you can, I will tell you that during phase 0, the funny current and the transient calcium current stop due to closure of their receptive channels. Now, depolarization during phase 0 causes gradual opening of delayed rectifying potassium channels, which will play the major and the main role in the next phase, phase 3 of repolarization. وبناء عليه فإن علينا أن نعي كل الوعي أن أثناء phase 0 الفاني تشانلز اللي بتعمل الفاني كارنت بتاع الصوديوم والترانزيانت كالسيوم channels are going to be closed and the flow through them will stop because these channels are closed. يبقى phase 0 خلاص قفلنا الفاني channels وقفلنا الترانزيانت كالسيوم channels. في أثناء حدوث ال depolarization during phase 0 في آخره هيبقى فيه gradual opening لنوع جديد من الريكتيفاينج اللي هي بتعمل correction وبتعدل وبتظبط rectifying potassium channels will open، وهتكون دي هي المسؤولة عن عملية الريبولاريزيشن اللي هي في phase 3. Slide 48. Basically, phase 3, which represents the repolarization phase of the action potential, it occurs, as we said, due to opening of delayed rectifying potassium channels, DRK, leading to increased potassium conductance, potassium outflux. This leads to outward direction potassium current that leads to repolarization. The outward flow of potassium occurs along concentration as well as electric gradient. Slide 49 provides you by basic understanding of what's really happening in phase 3, that you have to remember that at the same time of potassium efflux, the L type of calcium channels become inactivated and close, and the repolarization continues until the membrane potential reaches the minus 60 millivolts. At this potential, the outward potassium current becomes gradually inactivated, while the inward sodium current becomes activated again due to opening of the funny current channels, as you remember, and the cycle is repeated again and again, over and over. This brings me to the end of my presentation. I wish that I could clarify as much as I can of this part of the cardiovascular system as an important beginning. and I hope that everyone could understand every word I said. And in the end, I wish all of you the best of luck and the best of everything. Thank you.